Where are you?
Is it on?
Everyone's done. I just that's good. But I will start from now on. Okay. December.
Normally you watch
I think I have. I still play class.
Yeah, you do.
But you know what? If I were in the class, I would. But
You would have been.
yeah,
Yeah, that's what
I just listen to them. That's better.
Where did you meet this? Where did you meet this girl?
Yeah, one of my friends lives in Korea.
I know one of your classmates. It's a Korean.
No, it's half 7. I was saying 7 to you, so you get half 7. Yeah, I don't know what we're drinking. I don't know if we're going to pub or what. I was like, it would make more sense because it's still cheap and it's more atmosphere. But that's what I was going to ask. That's what I was going to ask. When I leave at 1 o'clock, I'm just going to put in the group like later or 1 o'clock. Because we can pre-drink a man, that's fine. But the problem is, it's
I like halfway to the end.
we need somewhere that's exciting.
Yeah, halfway.
Smiling.
I think it works on that this week.
Yeah, it's new. Near the gate.
I'm almost done.
Really?
Yeah. I will not. I will not. I think it was a thing. Two, three.
내가 봤을 때는
That's why you're afraid.
I went back to my home at 6 a.m. What did you do last night?
Are you ready for the presentation for the
Good luck.
When did you start? Was it like in London? Okay, good afternoon everybody. Sorry, it's a slightly late start. If you remember, we were talking about different modes of localized corrosion, and we had just started to look very briefly at the combination of corrosion and stress. And there are three formats of that. Stress corrosion cracking, which we're going to talk about first, which has a static load applied at right angles to the crack growth direction. Corrosion fatigue, where you've got cyclic loading, again at right angles to the crack growth direction. And hydrogen embrittlement, which isn't a corrosion process, but has this common crack growing at right angles to the loading direction within it. And that's what we're going to talk about. Stress corrosion's been around for a long time. It first appeared back in the late 19th century, and was first recorded as a thing called seasoned cracking, which I'll describe in a minute. So seasoned cracking is quite interesting. It was observed in the artillery shells of the British Army, and in the campaigns that were run in humid environments in India and various other places. In the turn of the 20th century, artillery were pulled by horses. So you had cannons, shells, and horses, and men, of course. And the brass shell cases were made out of thin drawn brass, and what they began to find was that the shell cases were cracking in the arsenal, in storage. And this was a major problem, particularly during the humid part of the year, hence the word season cracking, because it happened when there was a high moisture level. And armies being armies, they always have a standard format for doing things. So the officers' mess is over there, the NCOs have a mess somewhere else. The horses are always stabled there, and the arsenal is always put in a particular location as well. And as luck would have it, the arsenal was next to where the horses were being stabled. And that was the same in every camp that they had around the place. As soon as you got a humid environment, the manure that the horses were generating has an ammonia content to it, and the ammonia combined with the moisture gives you ammonia cracking of the brass. Extremely serious situation, because you're then out in the middle of somewhere on a campaign and you actually don't have any ammunition. So highly embarrassing. You have to keep it very secret, otherwise you get wiped out. This sort of season cracking, as it's called, occurs in all sorts of brass devices. This is a bit of a thin-walled telescope tube. It's brass drawn tube rather than an artillery case, and some of it's quite good, but other parts have very large hairline cracks in it. Don't crunch the tube, it's a reasonably old tube, but that's the sort of cracking that you get in the material, which just means that the cases, the artillery shells, were useless. So that's the origin. It was identified as a combination of the residual stress in the brass, because it's been heavily worked to make a thin tube, and the ammonia from the manure. And even today, in refrigeration systems that use copper alloys for piping, there are problems with ammonia and amine cracking of the copper pipes. So the problem's still with us in a way, in a slightly different form. There's been a lot of work done on stress corrosion cracking, and there's several mechanisms at play, and they all overlap. So you get a sort of spectrum of mechanisms that run from mechanically dominated, i.e. the stress is the most important factor, to dissolution dominated, where the stresses are low and the corrosion is the fastest component of the combined action to give you cracking. So the guy that put the concept of a spectrum of mechanisms together was called Redford-Parkins, and if you get keen, you can read his papers on not just mechanisms, stress corrosion cracking, but also on pipeline steels. They're not an easy read, I have to say, but there's some really good quality stuff in there from the 70s through to the 90s. Before this concept of a spectrum of mechanisms arose, everybody was fighting with each other, saying, oh, stress corrosion cracking happens this way, no it doesn't, it happens this way, no it happens, and so there was a lot of argument going on, but in fact it depends on whether you're a mechanically dominated situation or a chemically dominated situation as to what the mechanism is. The worst thing about it is you've got a component that perhaps superficially looks perfectly good, but is full of fine cracks, and that leads to all sorts of major failures. And the sort of things that you see are things like this. This is a photograph of the remains of the nylon manufacturing plant on the River Trent called Flixborough. It's a famous disaster site, and what they had there was some alteration to the plant. There was a bypass pipe put in, and that then failed. And the leak of the raw component, the cyclohexane, into the plant caused a massive explosion and flattened a lot of the buildings in the structure. So you can have quite dramatic failures, and that isn't good news at all. This is another one a little bit closer to home for you guys. This is a photograph, an aerial photograph of the major explosion that happened in Canada in 1995 on what they call the Trans-Canada Pipeline. So this is a major oil route. These are trees, okay, which gives you an idea of the scale of the crater generated by the explosion. Trans-Canada Pipeline was really where all the interest in stress corrosion of pipeline steels kicked off from. In the mid-80s, there were 3 failures of the pipe without explosions due to transgranular stress corrosion cracking, cracks running through the grains. And quite often, if the cracks are running through the grains, not always, but quite often, that suggests a mechanically dominated attack. They then had a couple more failures in the early 90s, and then this explosion in 95. And that kicked off a whole lot of research and questions about monitoring pipelines, oil pipelines for safety. Don't need any of the details of this, I just wanted to show it to you. This is a fairly elderly table, but what it does is it lists the environments in which you can get stress corrosion cracking. And the only reason why I put it up is to say we tend not to have either heard of stress corrosion cracking, or we tend to think it's not very common. But in fact, it appears in all sorts of industries. And if you look at this list and you go to ordinary steels, you'll find that actually the bicarbonate solution or hydrogen carbonate solution in groundwaters that causes cracking of pipeline steels isn't even listed there. So there are a lot of things that aren't even on this table, and the table's already got quite a lot. So we get a lot of cracking in Inconel alloys, in power generation systems. We get a lot of cracking in steels in a whole range of environments. And so it's really much more common. And the failures you get, you've got to inspect vigorously for, because your superficial appearance of your component is that it's all right, but it's actually got a hairline crack in it, and it's waiting to fail. There's a lot of discussion about how cracks start. This is an image, an aerial view, so to speak, looking down, and then a sectional view of a pit in some stainless steel in a particular environment. We needn't worry about that. There's a certain number of people who believe that you've got to have pits before you can have cracks. There are other people who say, no, you can actually have either. Sometimes you get cracks without any pitting, sometimes you get pits without any cracks. So this is a cross-section of that pit, okay, sectioned along that line there, and there aren't any cracks radiating from the bottom of that pit. Yeah, so you've got a pit without a crack, which is okay. This is the same material, okay, so it's the same alloy, and in this situation, it's a stainless steel 316 actually. Here's a pit, plan view of it. There's the section, and this time the pit's got a load of cracks growing from it. So sometimes you get pits, sometimes you get pits and cracks, sometimes you just get cracks. And some of them, I have to say, are really beautiful. So this is a montage of the cracks radiating from a pit in stainless steel, and it's just like a tree growing. It's lovely, isn't it? It's pretty good, I think. Okay. And I suppose I might add, we mentioned, I think last time briefly, the two types of cracking. So you get transgranular cracking and intergranular cracking. This branching effect that you get and the slight kinks in the crack are indicative that it's intergranular. Okay. So I think that was the slide that you had at the end of last time. Yeah. Just reminding you had transgranular and intergranular cracking of materials. Okay. So what's happening in the stress corrosion cracking? One of the most common popular models is this one called the oxide film rupture model. So in stainless steels, you've got a chromium oxide surface layer, and oxides are generally not very ductile. They're brittle in comparison to the bulk metal underneath them. So if you apply a stress to the component, then the oxide film will rupture. It'll brittle fracture, exposing the metal underneath. And that's true also for the passive films on iron, magnetite being the most common, Fe3O4. So once you've got a system where the stress is breaking the oxide layer, that's a way of localizing all the corrosion in the point where there is a fracture in that layer. And the vision is of a sort of stepwise process. You break a hole in the layer, you get a little bit of corrosion, it passivates again, the stress breaks that layer, corrodes again, it passivates again, and you get a progressive growth of the crack. Your handout actually illustrates what's going on more or less in the stress corrosion cracking case on the left-hand side of the diagram. All I've done here is added an extra line to indicate that the surface, the external surface and the side walls of the crack passivate. So that blue line is the oxide, which means all the current is concentrated to the tip where there's low oxygen. So this is the anode, relatively high oxygen on the outside of the structure. And you get some corrosion. This will then passivate, the stress will then break that oxide, and you get a series of progressive steps of corrosion. The case on the other side we'll come back to is the hydrogen embrittlement, but this diagram's quite nice in that it does actually illustrate on the bottom that for stress corrosion and indeed for corrosion fatigue to occur, and all our other localized corrosion mechanisms, we need an anodic current flowing in the material. Whereas for hydrogen embrittlement, it's a cathodic process. Yeah. So there's quite a difference in the potential on the surface of the material. One's anodic and the other's cathodic. Well, I'll show you a couple of samples. These are they're actually scaled down compact tension specimens. These ones are actually of a weld. Okay, so what they call a transition weld between two different types of material. There's a notch put into them, and then there are loading bars put into the top and bottom, so you can pull the block open. It's been exposed to a corrosive environment, an environment which causes stress corrosion cracking. And the interest was where do the failures occur and what happens. It is actually a weldment. It's a join between two different materials. As it happens, the crack runs along the weld interface, which is not particularly surprising considering that's where we notched it at any rate. But we were looking at how you modify the environment to modify the amount of cracking and get how early the onset of cracking occurs in the material. So one's a block that was tested but didn't actually crack. The other one is one half of another specimen that did crack. And what I hope you're going to see here is that there's an area that is coated in magnetite, and that's where the crack's grown along through the weldment. And then what we've done is we've put in liquid nitrogen and broken it open. So the end bit is what they call the brittle fracture, where we've just broken the specimen open so that we can see where the crack front is, how far the crack's gone through the material. And the answer is it's to the end of the black area of magnetite. So it just gives you an idea what sort of things you can do. The ripple is because of the weld. This is another failure. The intergranular failures are always the nicest ones. They've got a lovely crystalline appearance to them. This is a stainless steel fitting from a company called Swagelock, who make a lot of pressure fittings, and this is caustic attack. So sodium hydroxide, potassium hydroxide alkali attacks stainless steels, as do chlorides. So that's a quite nice intergranular failure of a stainless steel. But you guys don't really want to know about stainless steels, you want to know about pipeline steels, so let's say something about them. Actually, I'll pass another one round just for you to look at. This one's a little bit different from the first one because it isn't a weld. Okay, it's not a seam, it's a bulk material. And what you'll see when you look at it is we've done exactly the same thing. We've grown the crack through. It's got oxide on the sides of the crack because it's passivated and only the tip's been attacked. But the boundary between that and where we've cooled it in liquid nitrogen and broken open is now shaped. It's now shaped like that. And that's generally what you get in a bulk material. On the welded sample, the crack front is flat. On the weld, this is the darkened area, and that's purely because of the weld ripple. This is the more normal crack front. You get a curved crack front. But it's the same thing. The sides of the crack are passivated, and the tip is the only bit that stays active and corrodes. So the intergranular attack in the alkaline conditions, that had been known for quite a long time, since the mid-1960s. And people thought they'd got a handle on that and understood it. It was the transgranular cracking that started appearing in what they call the near-neutral solutions in the 1980s and 90s that rather scared the people involved in oil transportation. And the change of the groundwater from this alkaline condition, which hydrogen carbonate is naturally in, to this near neutral environment is related to the evaporation and cathodic protection system applied to the pipe. So they modified the environment almost by accident, and that led to another mode of failure, a transgranular failure instead of an intergranular one. Just going back to the crack shapes for a minute. The cracks are very interesting because the crack front, you know, where the edge of the crack is different under different conditions. It knows about the stress field. It senses the stress field, and it knows when it's getting near to the edge of a body, a component. And cracks actually change direction and things. They respond to the stress field, and they respond to the shape of the component. And that's why those particular specimens are fairly long in comparison to their width, because we're interested in the crack growing along and not hitting an end wall, not getting interfered with by the end wall. You still get some shape to the crack front, and in a sense the crack is growing faster in the middle than it is at the edges, because the stress field is different. And you get that with all sorts of components. So if you take a tensile specimen, if you just take a round tensile specimen, okay, and look at it through the section, if you get cracks in there, they will be of that sort of shape. If you get a square section specimen and you look at it, they end up being hemispherical. Okay, the cracks come in from the corners and they grow in a hemispherical shape, whereas if they're on a round surface, then this is aspect ratio is about they call them thumbnail cracks. It's about a ratio of about 2 to 3, something like that. So crack shape relates partially to the dimensions and the stress field in the material that is growing through. Now you might merely say, oh well, if the pipes are being cathodically protected, then how do you get anodic stress corrosion cracking? And the answer is that in the bottom of a capillary, you might have a negative potential out here on the bulk surface, but at the bottom of a capillary the potential can be entirely different. It could be positive. Okay, because this thin area of solution in here has a high resistance, and you don't get good potential control from your bulk CP system down a crack. It just doesn't happen. Okay. The other thing, of course, is that this solution in here, not only is it low oxygen, but it starts to change composition. Remember, in the anodic reaction, you begin to produce acidity, because when you produce, first of all, some corrosion, so you get iron 2 plus or iron 3 plus or whatever the corrosion product is, and when that forms oxide, we want to form Fe3O4, so this is a mixed iron 2, iron 3. Then we also produce some acidity when the oxide forms. It's called hydrolysis of the ions. So the composition of the solution inside the crack is low oxygen, higher acidity, and there will be some other differences between the bulk solution and the interior solution. And that all contributes to changing the potential down here, despite the fact that the bulk potential appears good on the outside of the surface of the bulk component. Yeah. Yes, sir.
So, other than the pH regions, what other environmental factors would point towards a high risk of stress corrosion cracking? Because I can see that those could occur in any pipeline system.
Yeah.
It doesn't always happen.
No, it's true. You've got to have a number of factors, and actually, what you're trying to do is get a balance between the formation of a passive oxide. So you've got to have some mechanism to get passivity into the material. In a steel, it has to be Fe3O4. So you've got to have the right environment to generate a passive oxide. You've got to have the correct balance between the rate of loading, the stress that's being applied, and the speed of the corrosion. So there's got to be a balance between the mechanical loading and the speed of corrosion, because if the corrosion is too fast, you just passivate the whole thing so quickly that it never really doesn't get a chance to grow. If the stress is too high, you end up with a brittle fracture rather than a crack, because the corrosion doesn't get time to occur. So there's a balance between a number of factors, and people tend to think, oh, right, it's stress corrosion, therefore you should use a corrosive environment. And I used that word earlier on, and I corrected myself. They're not really corrosive, not like acid. You're not getting an enormous amount of corrosion. What you're trying to do is build up a passive layer on the surface of whatever the oxide is, so that you can then rupture that oxide film and get localized attack in one area. So it's got to be a balanced system. These are some sections from tensile specimens after test, just to illustrate what's going on. This is X100, which is one of the higher grade pipeline steels that are beginning to come online. And what we've got is intergranular cracks in the section of the specimen. So we've sliced the specimen. These are individual grains, and you can see the crack is moving around the grains. So that's intergranular failure under one set of conditions. And the same steel, this is the transgranular version. Admittedly, these cracks aren't very long, but this is one grain, and the cracks are growing through the middle of the grain. They're not travelling down the grain boundary. Yeah. So it's possible to get transgranular cracking and intergranular cracking in the same steel, and the variation of that is because the environment is somewhat different. Yeah. And that can, when I say environment, that can be the solution, but it can also be the potential on the specimen. So what quite often happens is, as you go to, as you change the potential, you can move from a intergranular to transgranular cracking mode. And I'm just trying to think how that goes. The more anodic you go from the free corrosion potential, the more likely you're going to get intergranular cracking. So intergranular is corrosion dominated, and transgranular is more mechanically dominated, but not always. Okay. Yeah. The cracks are quite dangerous because after they form, they can join up. You get a thing called crack coalescence. So what we've got here is a sketch of a bulk material, the couple of cracks growing in from either side. This is the stress at right angles to the loading direction, and as the cracks begin to pass each other, they actually sense each other's stress field and turn in and begin to move towards each other, even though they're no longer growing at right angles to the stress field, and they will actually join up. And suddenly you've got damage to the component that's double the length that it was before. So you can see that the crack growth it becomes exponential, because the next time one of these joins on, it'll be 4 times the length, and then it'll be 16 times the length, and then it'll be, yeah. So the crack growth becomes very dangerous. The next time we'll talk a little bit about looking at the dissolution rate, and that gives you an idea of how to calculate out the rate of growth of the crack. But as soon as they join together and you start doubling the rate, start getting this exponential growth, it gets out of control. I thought what I should do is show you some fracture surfaces, in case you haven't seen any at all. Hopefully some of you have seen some fracture surfaces. Yeah. So this is ductile failure, okay? Classic ductile, yeah? And all you've got is what they call microvoid coalescence. You've got a little honeycomb network of ductile overload. That's intergranular. It does exactly what it says on the tin. The cracks are growing down the grain boundaries, and you can actually see individual grains on the surface, which you could probably see on that stainless steel specimen that was going around if you looked at it carefully. That's a transgranular failure. Quite different in that what you've got is flat shear planes through the material. So you can't see individual grains. What you've got is a series of big flat sections, sometimes at slightly different angles to each other, but not this business of, right, it's going round the grains. So it is quite different because you've got these flat facets to the fracture failure. Okay, and I think that's not a bad place to stop. See you next week. Thank you.
I want to discuss about this occasion.
Okay, yeah.
Next week.
Yeah, sure.
So I will email you.
Yeah.
Actually, my topic is what is what you like on
Okay, yeah. Yeah.
I want to know how to make the corrosion, different corrosion kit.
Okay.
Is this one because of cracking? I mean, because of corrosion?
Yeah, alkali attack on stainless steel.
Okay.
That's stress corrosion cracking. Because the fitting, you see, what was screwed onto there gave the stress, and then the crack grew in at right angles to it. Because this was caustic solution in the inside.
Okay.
Yeah, the chemical plant example.
Excuse me, what's the name of this crack when the bottom is like this and when it is sharp?
No, don't. I haven't talked about that really.
Yeah, I know, but do you know how you can call when the bottom is sharp like this or when the bottom is curved?
Well, if it was curved, you'd say it would be radius.
Radius.
If that's what you
This
mean.
just sharp cracking, yeah?
Well,
I mean the type.
you've got to be careful because sometimes in stress corrosion cracking, not always, they look like this. Sometimes.
But sometimes it might be like this.
Yeah. If you get, the more corrosion you get, the more rounded it looks. The less corrosion you get, the more pointed it looks.
Okay, okay. Yeah.
Can I visit your office to ask about the corrosion fatigue?
Sorry?
Can I visit your office to ask about corrosion fatigue?
You can ask me, yes.
Really? Because now I think there is another class.
Yeah, send me an email.
Really?
Okay? Yeah.
Is it possible to just visit now your office to just a simple question about the corrosion fatigue because I think it's a little bit related to my dissertation project. Because I'm thinking about the crack in corrosion. I'm just understand about how can crack can be developed in the corroded area and then what the effect of corrosion on the crack growth rate.
Yeah, well, you're going to see next week, we're going to talk about the Faraday's law and how it affects, that's what controls the corrosion rate. And then it's a question of the crack tip surface area. You know, the narrower the crack, the faster it goes. Yeah. So I'm going to talk a little bit about it, but not a lot.
That means on the crack tip, the corrosion, the rate, according to Faraday's law, it will affect the crack tip area. I mean the microstructurally, the crack tip will
Well,
be corroded.
it's how much is dissolved away is directly controlled by Faraday's law, yes.
So in that environment, the crack is not driven by only the stress, but also
No.
driven by the corrosion.
Yes. Yeah, it's a combination of the two.
I see. So because I saw in some standard, like for the crack assessment, there is something like what the degraded the coefficient about the crack growth rate, based on the corrosive environment, like because of the corrosion.
Yeah.
Is it something like that?
But it's a combination of the stress and the corrosion. Can't be one or the other. Come on. You know, it's combined.
Hello.
Sorry. Yattering away again.
Now, emotionally scarred. One. Last night.
Hi, is it okay, sorry about this, but is it okay for me and Scott to leave about half an hour early just because we've got some housing stuff to sort out and basically our estate agent didn't have time.
Well, you will have to catch up. Yeah,
We will
on
catch
your
up.
own. There's an awful lot of it, this class, but it's adjectives and stuff. But okay this time, but try and arrange it.
Oh yeah, we tried to.
Last time you couldn't do it any other time,
Yeah.
like today, and it was like
Okay.
really isn't very helpful.
Yeah.
Well, I trust